substitution, nucleophilic, unimolecular, or the SN1 reaction. So in any substitution reaction, you are substituting one group for another group. So in this chapter, we're looking at all reactions of alkyl halides. So our substrates would be an alkyl halide, something like this. And halogens make for good leaving groups, and that's because they are weak bases. So a good leaving group is a weak base. And so if you have a good leaving group, a nucleophile can replace it. And we have two mechanisms that we will see for substitution. We will see this unimolecular or SN1 reaction, and we will also see the bimolecular or SN2 reaction. So those terms, unimolecular and bimolecular, have to do with the rate determining step of the mechanism. So I'm going to go ahead and draw the mechanism for this reaction. And so we are starting with the tert-butyl chloride. And in an SN1 reaction, this unimolecular refers to the rate that there's only one molecule, and that's the alkyl halide, that's involved in the rate determining step. So when you have a tertiary alkyl halide or something else that can form a stable carbocation, you will see an SN1 substitution take place under the appropriate conditions. And so in this mechanism, what happens is the molecule first ionizes. The leaving group leaves, forming a carbocation. So the only substrates that can undergo this SN1 reaction are going to be ones that can form stable carbocations. So the ideal substrate for an SN1 would be something like a tertiary alkyl halide. That would form a relatively stable carbocation. The other way a carbocation could be stabilized would be through resonance. So we could also see benzylic and allylic alkyl halides undergoing this reaction. Okay, so this first step here, this is what the unimolecular is talking about. This is the slow step of the mechanism. And so the rate only depends upon what is involved in this step, which is just the alkyl halide. So for an SN1 reaction, the rate of the reaction is equal to the rate constant times just that alkyl halide, because that is the only thing involved in the rate determining step. Okay, and so continuing on, after you form that alkyl halide, a nucleophile is going to react with it. So in this case, we have water as a nucleophile. So water has lone pairs of electrons on that oxygen, and so that can bind to this carbocation. And when it does that, this carbocation is flat, so it could attack from either side. This would be significant if you had 4 different groups on that carbon atom, because that would mean you're forming a chiral center, and you would end up with equal amounts of both enantiomers. Okay, so let's draw the product of this step. So we have a new bond between the carbon and the oxygen that we formed with this arrow, so there it is. And the water molecule also had 2 hydrogens, so they are still attached. And so we have this protonated alcohol. This is not our final product. The final product is going to be one where we deprotonate this. And so the water in this reaction is playing the role as both the nucleophile and the solvent. So this is a reaction known as a solvolysis reaction. And because this is the solvent, it means you have just a ton of water around relative to anything else. That's why we see the water attacking rather than the chloride reforming, because you just have so much more of it. And so it's going to be the water that we're also going to see act as a base to remove one of these 2 acidic hydrogens and give the alcohol as the final product. All right, so there's another water molecule, and we can remove a hydrogen and have those electrons come back to that oxygen. So we will form the product. So we're going to put a note about the stereochemistry here. So stereochemistry. So if this reaction is taking place at a chiral center, in this example it's not, those are all methyl groups, but if it were at a chiral center, so if the reaction was at a chiral carbon, you would get a mixture of stereoisomers formed. And that mixture of stereoisomers, again, comes from the fact that you go from a tetrahedral carbon to a trigonal planar sp2 hybridized carbon. And so that's flat, and your incoming nucleophile could attack from either side. Okay, and so moving along, so we've covered the mechanism and the rate. The ideal substrate, as we mentioned, for an alkyl halide is something that can form a stable carbocation. That's how we ended up with this list. So tertiary alkyl halides, benzylic alkyl halides, and allylic alkyl halides can all undergo that SN1 reaction, and that is because they can form stable carbocations. The nucleophile for an SN1 reaction, although it is not involved in the rate determining step, to avoid a competing elimination reaction, the nucleophile for an SN1 reaction would have to be a very weak base, weak nucleophile. If you have something that is a strong base, or even a moderately strong base with something like a tertiary alkyl halide, the elimination pathway, E2, would be favored. So to have this occur, we want a weak base, weak nucleophile, and essentially the only ones you're going to see, for the most part, are going to be things like water or some simple small alcohols, right? So if your nucleophile is water, you'll end up with an alcohol as a product. If your nucleophile is the alcohol, you will end up with an ether, because at this stage, essentially, you would have the R group here, you'd have an oxygen that's protonated, and when you're trying to neutralize something, you'd be taking off the hydrogen, right? When we think about acid-base chemistry, we're usually talking about moving around hydrogens, looking for acidic protons. Okay. The temperature of this reaction. So this is a consideration if you want to think that an SN1 substitution under these conditions might potentially compete with an E1, right, which would be the unimolecular elimination. So we would note that E1 would be favored at higher temperatures. So if you were using this list to decide a reaction pathway, you'd be first looking at the substrate to see what sort of reactions were possible, and then look to the nucleophile to see what you're reacting it with. And so if you have something that forms a stable carbocation, you've got a weak base and a weak nucleophile, the next thing you want to look at is just make sure it hasn't indicated that we're heating this up. If we were heating it up, that would probably be an indication that we're going to go through the E1 pathway. And finally, the solvent. This is not really important in determining the reaction pathway, but it can have an influence on how fast the rate is. And so the solvent affects this reaction in terms of the ability of the solvent to support that slow step. The slow step of the mechanism is an ionization, and it forms a positive charge and a negative charge. So if you have a solvent that can stabilize both cations and anions, it will support this slow step, lowering this activation energy barrier, and will make the reaction go faster. So this reaction will be faster in a polar protic solvent, right? And a polar protic solvent would be something like the solvents that we see for solvolysis, so things like water and alcohols.